Uh, Good morning, and I should start by thanking the organizers for this opportunity. And so I'm going to basically talk about deep learning assisted detection and termination of spiral and broken spiral waves in mathematical models of cardiac tissue. Okay, so I'm Jaya Kumar. This work is done in collaboration with Mahesh, a graduate student, and with Rahul Pandit at IISc. So and this work is up on archive. You can go look at it for more details. So let me start with a simple reaction diffusion model. So we basically look at these set of equations, two variable equations, and we have a diffusion term and then a nonlinear term over here. These set of variables mean different things for the cardiac problem, but let's just look at these two set of equations. Over here, this is a kind of a general formulation that we look at, wherein f and h are going to be nonlinear functions. So let's look at what are the nonlinear functions for our problem. So there are a lot of different models which people have studied in the literature. Two variable models over here, different names of authors, and realistic models over here. I have mainly concentrated on two variable model, and I'm damn scared of these set of models over here. And this is where Mahesh comes in and helps us out with working with all of these models, and I'll let you know why I'm scared of these models. Okay, so if you look at these set of equations, they do have solutions which give us wave equations. So if you look at this, let me run this video. It has some issue with this. So if you look at this, it's a plane wave equation. It has a plane wave solution, but by giving different kind of forcing it, we can make it into a spiral. This is what we call as a auto wave, which basically sustains itself and keeps running forever. Okay, so this is one set of solutions, but then you can even have, if you tune the parameters enough, the same spiral wave can break into multiple spiral, and this is a chaotic regime. Basically, you'll find that we have done nothing. The spiral wave continues, and it by itself breaks up into multiple spirals over here, and you'll see a beautiful structure forming over here. So these are the solutions of these set of equations. So why are they important? You'll find that these are used to model heart, cardiac tissue. So one of the models, the realistic model, that TP06, you can run it on an anatomically realistic model. Again, a simulation which was done in Rahul's group, which will again show spiral waves. But then, okay, so if you want to look at these set of equations, this is why I'm scared of it. It has got 40 variables, 26 different set of differential PDEs. Okay, you need to solve them simultaneously, nonlinear set of equations. So I'm not going to do it. Mahesh has taken care of it for me. And then we basically look at what do they do. Even these set of equations give us spirals and broken spirals. So why are they important? You'll find that these are the ones which lead to these kind of diseases, ventricular tachycardia or ventricular fibrillation. So we need to get rid of these kind of solutions in the heart tissue. So how do you do it? So if you look at in how is it done normally? Okay, if a person gets these kind of waves in their heart, basically a patient is dead in 2 minutes. So you'll see that the usual defibrillation method is this, wherein you basically give a shock to your chest, right? You must have seen it in movies. Basically, this is around 11 kilovolt shock. And you think that people do it very often in movies. You will find that doing this will basically create scar tissues. And that scar tissue will later on make it worse as you go along. You'll be more prone to similar attacks in the future. So we don't want to do this. We want to reduce the voltages. The same thing over here, you can nowadays have something like a pacemaker which you install within your chest, which also does something like this, but with a lower voltage. Okay, now so we don't want to do this. We want to reduce the amount of voltage that is applied. So how do you model it? Model this defibrillation, the usual defibrillation is just by adding this extra current to the equations. So if you look at this, now I have initialized the spiral wave, and then uniformly I apply a current and it gets killed. So it gets killed, fine. Now I don't want to apply uniform current for the whole system. What I'll do is I'll try to apply it locally as a Gaussian. So you'll find that in this particular case, this is run in a MATLAB, so you'll find I'll go locate the spiral tip and apply a local Gaussian current over there, and it gets killed. So I have reduced the amount of current that is required. But then if I try the same thing with and try applying the local Gaussian not at the spiral tip but at one of the arms, you'll find that it doesn't get killed completely. So the whole point right now is I want to detect the spiral tip and go apply the current over there locally, Gaussian current, so that I can reduce the amount of current that is applied. So now the problem has been reduced to detecting these spirals. So you'll find that in heart you have multiple spirals. So if you look at it, there are lots of different varieties of spirals. These are all coming from different models, all realistic, the simple model and all that. And these are wave solutions which are not like spirals. These are like target waves and plane waves. We don't want to disturb this. Whenever we find these kind of spirals, we want to kill them. Okay, we want to locate the spiral. And how do you do that? There are techniques to do it in literature. For simulation, you can find the tip of the spiral. But then if you look at it, experimentally, it's not that clean a spiral. It has got a lot of noise in it. So in the case of noise, in the presence of noise, most of these algorithms don't work. And this is where we realize that the best approach would be to make use of some kind of image processing algorithm, which is very often used in computer vision kind of thing, wherein you want to, given an image, you want to say whether it's a car, truck, or bicycle kind of thing. Okay, so this is basically called convolution neural network, a very classic problem which has been solved in the field. So basically people do use these kind of algorithm in critical applications like driving of cars and other things, but okay, there are a lot of jargons involved, so I'm not going to bore you with all the jargons. All that we want to do is, given an image, we want to say whether it's a car, bicycle, or something like that. For our problem, we modified the structure, and we basically want to say that give an image and say whether it's spiral or not, so that we'll be able to detect the spiral. So here, the way that we are going to do it is, we are going to train the network by giving a bunch of data which basically is already classified as spirals or non-spirals. This you can generate it, generate these kind of data from different models, and then if you, in some sense, what this network basically tries to do is some kind of curve fitting. You basically have a energy cost function which is like an error, and you want to minimize it, and this falls under some kind of a non-convex problem which can be solved using stochastic gradient descent method. Now the important point is that you need a huge amount of data. Over here you'll find that 22,000 images, and these are all generated from simulations, and you need to already classify them for training, and then you basically train them and test them. Okay, this is like you have a huge number of questions, but then you don't ask all the questions to the as assignment. You ask few of them and then use the extra few to test how well did they understand it. So that's the validation part, and it actually gives 99.6% accuracy. This is an amazing accuracy which we didn't expect to start off with. Okay, the next thing that we didn't expect was we basically trained a spiral and these kind of bunch of waves. But then when we tried giving a broken spiral, a much more complex structure over here, it turns out that it gets classified uniquely with 99.4% into a spiral. Okay, so it works really well. And then now what do? Okay, we have managed to detect the spiral. Okay, the next point is to basically locate the scores of these spirals. So how do you do that? Basically what you do is you take up this huge image and scan through the image. You pick out small blocks of these images and feed it to the network, and basically says either a spiral or not a spiral. And then you basically build something like a heat map. Over here, you scan through the image at different overlapping version, or even with different sizes, you can zoom in and zoom out, and then basically generate this heat map. And now the whole point is that this acts like a probability of the core of the spiral over here. If you use this as a current and apply it to the tissue over here, ideally this should kill the whole structure. And that's what we want. But from practical point of view, we thought that, okay, instead of trying to apply it all over the place, we'll build an electrode kind of structure with dot matrix electrode over here. And what we would do is, so this is the input signal, we've generated the heat map, and then from the heat map, based on wherever the heat map is hot, we basically give a higher current or voltage at those electrodes. And then, so this is the impulse that we are going to give to the tissue over here. And this is what happens. So you'll find that starting from this particular pattern, if you apply this particular current, you'll find that over time it basically kills the whole structure, and thus we can eliminate the whole spiral structure over here, and we are safe. So, and okay, so here there is some kind of comparison to say that with the earlier work, to say to claim that we are doing it much better in terms of lower current value, so it's better to use this kind of this algorithm. Fine. So let me just conclude by saying that we have managed to do spiral detection as well as defibrillate remove the spiral structures over here. And let me just point out that these kind of structures can be generated even in our tabletop experiment with BZ reactions, which Mahesh has managed to do very recently. And you will find him demonstrating all of this in open day. Do visit us if you are in Bangalore, which is on 29th February. That's it. I think, thank you. Questions?